Hey guys, welcome back to the Career Guide Academy. Let's start with the today's third lecture of electrostatic, in which we are going to learn about the Coulombs Law in vector form, superposition theorem and some numericals based on them. So now whatever we have learned in Coulombs Law, that is for the two charges. So let's consider we have more than two charges in the system. Let us say this is Q1 charge which is at a point 1. There is another Q2 charge, let us say at point 2, and there is another third charge, let us say at point 3, and its charge is Q3, right? Now, if I want to find out the total force which is acting on the two, right? So, as of now whatever we have learned, that for the two charges, we can find out the net force, we can be able to find out the force between the two charges. We cannot find out directly the force between the three charges because we don't have formula for that. So for that purpose we have to use the superposition theorem. So what superposition theorem states? If the person standing towards right, it is pulling me with a 10 Newton force, and the person who is on the left, if he is pulling me with a 5 Newton force, obviously on me there will be a 5 Newton force which is towards right. Clear? So basically we have to add both the forces but vectorially, right? So why vectorially? Here it is very easy, sir, we have to subtract. Okay, so always subtraction will not be there. If both the persons are pulling me in one direction, then they will get added. That is also simple, sir. Then if this fellow is applying 5 Newton force, this fellow is applying 10 Newton force, then obviously I'll be moving not towards right, not towards front, I'll be moving in between these two forces with certain magnitude that can be given by addition of the two forces, but that addition should be vector addition, right? And this is nothing but our superposition theorem. So whenever two forces are acting on one body, right, then the net force that is going to act, it will be the vector addition of individual forces which is going to act on that body. So let's see on the board. Let's consider we have Q1 and Q2 charge in the system only. If we consider only two charges are there, then it is very easy to find out the force between them. So Q1 and Q2, that force I can represent directly. The Q2 is going to get repelled due to the Q1 charge in right side direction, and what will be the force on it? That will be the force on 2 due to 1, it is in this direction, and what will be its magnitude? That will be equals to K Q1 Q2 divided by the distance between them. So distance between them, let's assume this is R12. So distance between them is R12. So I have to take R12 square. So this is the magnitude of force and its direction towards right. Okay. So this force is not going to affect by this presence or absence of this Q3 charge, and that is very important for the superposition theorem. Whatever forces are going to act on me that were independent, right, on each other. The force due to one person and the force due to another person was independent, right? He can apply 10 Newton force, he can apply 5 Newton force, both are acting on me, then also they will act their individual forces only. For example, if a young boy is pulling me towards right with the 10 Newton force, right, when this girl was absent, clear? Now, one girl is there, she is pulling me towards left with 5 Newton force when this boy was absent, right? Okay, now just think, if I am standing here, a boy is pulling me towards right with a 10 Newton force. Now that girl came and she started pulling me towards left with 5 Newton force. What do you think? What this boy will do? Will it pull me with a 10 Newton force? Maybe, may not be, we don't know. Means the force due to this person is got affected due to the presence of another person. right? Means whenever this affected part will be there, we cannot use superposition theorem, right? But what is the condition? The force applied by this person is independent whether this second person is present or absent, right? And in these cases only we can be able to use the superposition theorem, that is the net force we have to consider, that is the net force we have to consider. So what I am saying, the force on 2 due to 1, the force on 2 due to 1 is independent on the Q3 charge, is independent on this Q3 charge. Whether this Q3 is present or absent over here, this force is not going to affect, this force is not going to affect, right? So this force will be equals to K Q1 Q2 divided by R12 square only, right? Then what will happen due to presence of this third charge? Due to this third charge, what is going to happen? There will be another force on this Q2 charge. So let us say distance between them is R23. So what will happen? Due to this Q3, there will be another force on Q2 that will act along this line, and it will be repulsive as both charges are positive. So what will be there? The force between Q2 and Q3 will act, that will be the force on 2 due to 3, that will be equals to K Q2 into Q3 divided by distance between them is R23 square, right? So this force is also same thing, it is not depend on this Q2 charge, sorry, on this Q1 charge. Whether this Q1 is present or absent over here, this force is not going to change. So individual force between the two charges did not change, but what has changed? The net force acting on this charge has changed, right? Now here only we have considered the 3 charge system. Even though if there would be the 4th charge over here, Q4, then obviously these two individual forces would have not changed. What would have changed? There would be one extra force on this Q2 charge now due to the presence of 4. So if distance is 2, 4, then the force would have act along this line, and that force would be equals to force on 2 due to 4, that will be equals to K Q2 Q4 divided by distance between them is R24 square, right? So for the timing, if I want to consider the net force, then I have to consider the net force that is on 2, net force that is on 2, that will be the vector addition of all the forces, that is force on 2 due to 1 plus force on 2 due to 3 plus force on 2 due to 4. Like this, if there are n number of particles or the charges are present in the system, we have to consider the force due to all such particles or the such charges, which will lead us to the net force which is going to act on the one charge. So basically this is called as superposition theorem. What it is called as? Superposition theorem. So statement for superposition theorem is the net force acting on a charge, the net force acting on a charge is the vector addition of all the individual forces acting on that charge. It is the vector addition of all the individual forces that is acting on that charge. So this is about the superposition theorem. Let's start with the first numerical. In this numerical, it is given that one triangle is there. On the vertices of this triangle, right angle triangle actually, on the vertices of this right angle triangle, there are 3 charges situated, 1 coulomb and 2 coulomb, right? And they are asking us to find out the net force which is acting on this 2 coulomb charge. So let us try it. So if we want to find out the net force, we have to find out first what are the individual forces that are acting on this 2 coulomb charge. So first of all, let's draw this 2 coulomb charge over here, right? So if I want to consider this as 2 coulomb charge, right? on this 2 coulomb charge there will be a force due to this 1 coulomb charge which is situated at 3. So this third charge, it is positive, it is also positive. So this charge is going to repel this 2 coulomb charge towards left. So I have to show force on this, that is towards left. And what will be its magnitude? The force due to 3 on 2. So force on 2 due to 3, that will be equals to K. The charge is 1 coulomb here, here 2 coulomb. So Q1 into Q2, that will be 2 coulomb into here it is 1 coulomb divided by distance between them. So distance between them is given 3 meter. So we can consider that is 3 meter square. So it is 3 square. So we got the force on this 2 coulomb charge due to this third charge which is 1 coulomb. It is towards left, right? So I can write vectorially this force F on 2 due to 3, that will be equals to K 2 into 1. K value is 9 into 10 to the power 9. 3 square is 9. So what we are going to get? 2 into 1, that is 2. 9 into 10 to the power 9 divided by 9, that will be 2 into 10 to the power 9 Newton. This calculation you can pause and you can solve them, right? Okay. So this is about the force on 2 coulomb charge due to this third charge. Now let's find out force on this 2 coulomb charge due to the another charge which is present over here. So once again this is 2 coulomb charge. On this 2 coulomb charge, this 1 coulomb force is going to apply force in downward direction. It is going to push it because both are like charges. So force on this 2 coulomb charge, it will be in downward direction, and let's consider it as force on 2 due to 1. So its magnitude will be equals to K. Its magnitude is 1 coulomb into this magnitude is 2 coulomb divided by distance between them, that is 3 square. So if I put K value over here, once again what we are going to get? F21 9 into 10 to the power 9, 1 coulomb into 2 coulomb, that will be 2 divided by 9. If we solve this, we are going to get same answer which we got last time, that is 2 into 10 to the power 9 Newton. So this is the force which is going to act on this 2 coulomb charge, but due to this 1 coulomb force. So we have found what are the individual forces which are going to act on this 2 coulomb charge. So force we got F21, that is equals to 2 into 10 to the power 9 Newton. So we have found out the magnitude of these two forces. What about their direction? If I want to represent it in vector form, I have to tell its direction. Its direction is downward. So downward means we can write minus j cap. Its direction F23, that is towards left over here, means we can say it is towards left. So it will be minus I cap along the minus x direction. So we have represent the two individual forces in vector form. But we don't want to find out individual forces. What we want to find out? We want to find out the net force. So what will be the net force? So net force on 2 due to these two charges will be the vector addition of the two forces which are going to act on this 2 coulomb charge, right? So these two forces already we have found. If I write that forces, what we will get? 2 into 10 to the power 9, that is minus j cap, plus 2 into 10 to the power 9, that is minus I cap. So this will be the net force which are going to act. So we can say this is the force in vector form. But if I want its magnitude, how we can find out magnitude of any vector? That will be equals to under root x square plus y square plus z square, where x, y and z are the component of that force along x, y and z direction. So here net force will be equals to, magnitude of that force will be equals to under root x square plus y square, z is 0 over here, x and y are same. So if I solve this, what I am going to get? root 2 into 2 into 10 to the power 9 Newton. So root 2 we can put 1.41 and we can write 1.41 into 2, that will be equals to 2.82 approximately into 10 to the power 9 Newton. So this will be the net force which is going to act on 2, and this is our final answer, right? So we have used the Coulombs law as well as the superposition theorem to get the net force which is acting on the charge. Guys, let's start with the second question. So what second question is, there is a hexagon, a regular hexagon of side A. So on the vertices of this hexagon there are certain charges kept. So here Q charge, here minus Q charge, here 2Q charge, here 2Q charge, here minus Q, here plus Q charge, right? And what we need to find out? We need to find out what is the net force which is going to act on the small q charge which is situated at the center of the hexagon. So if we see this question, it is very easy question, right? Why I am saying it is very easy question? We have to think in different way now. If we consider the two charges, this is Q and this is Q, they will be exactly on the opposite side. They will be exactly on the opposite side. So we know the logic now. If we have some Q charge over here, right, and another positive Q charge somewhere here at a distance r. So this charge is going to push this Q charge in this direction with a certain force, that is F is equals to K capital Q small q divided by distance between them is r square. So this is the force which is going to act between these two charges. Now same charge if I keep at same distance but on opposite side, what we are going to get? We are going to get that the charge force on the small charge due to this capital Q Q charge, that will be exactly same because distance is same, charges are same, but it will be in opposite direction. It will be in opposite direction. So these two forces, if I say this is F1 force and this as F2 force, this F1 and F2 will be of same magnitude but they are of opposite direction, means they are in opposite direction, so they will repel each other, and what we will get, the net force which is going to act on this small q charge is 0. Now this logic only we have to apply over here. So if we consider this system on this q charge, this capital Q charge is going to apply force in this direction and this q charge is going to apply force in this direction. So the forces due to this q charges will be in opposite direction. So let's consider these are the F1 forces which are cancel each other, right? So if this logic you understood, now you can consider these two opposite forces. They will also, here this Q and this Q will attract because it is negative charge. So it will apply force in this direction, F2 magnitude. This will also apply attractive force in this direction of same magnitude, right? So they will also cancel each other. If we consider now this 2Q charge, this will also apply the repulsive force on this Q charge. Let us say that is F3 force in this direction, right? So this 2Q will also apply the same force in this direction. So even though this problem is looking complicated, but due to symmetry it is very simple, and we can say all the opposite charges force will cancel each other. So net force, this charge will going to experience the net force, that is if both forces are equal, the net force on this charge will be equals to 0. So in this case what will happen, the force which is going to act on the small q charge, that will be equals to 0, right? So this is about the Coulombs law in vector form, superposition theorem and the numericals based on this Coulombs law. Okay, so we are going to stop here today. In next lecture we are going to learn about the electric field. So stay tuned, stay blessed. Thanks for watching. Thank you.